Three men walked into a sealed workshop on a Tuesday morning and were dead before lunch. And the only thing investigators found out of place was a polished metal part sitting quietly on a workbench. No fire, no explosion, no broken glass, no signs of struggle. The ventilation logs showed normal airflow right up until the moment it did not matter anymore. The toxicology reports came back with results that made the lead examiner, a man named Dr. Harlan Voss, read the page twice and then sit down slowly in his chair. He had spent over 2 decades working cases involving industrial chemicals, heavy metals, solvents, gases. He had seen what chlorine does to a room. He had worked a case involving hydrogen sulfide in a drainage tunnel. But this was different. This was something that left almost no fingerprints at all, and it had used one of the most ordinary, most boring, most universally trusted metals on the planet to do it. Voss pulled the case file toward him and opened it flat on his desk. The workshop had been processing exhaust filtration components, standard industrial work, the kind of place where nobody thinks twice about safety because nothing on the shelf looks dangerous. The metal parts stacked near the workbench were a common alloy used in hundreds of manufacturing applications worldwide. You would find the same material in your kitchen faucet, in the zipper of your jacket, in the loose change sitting at the bottom of your pocket right now. But here is the thing that Voss kept circling back to in his notes. The workshop had a slow exhaust leak that nobody had fixed yet. Carbon monoxide was seeping in at low concentration. Not enough to trigger the detector. Not enough to cause any immediate symptoms. Just a quiet, invisible background presence in the air. The kind of thing that happens in thousands of workshops every single day without incident. Except that day, the temperature near the workbench had climbed. A faulty heating element on a nearby press unit had been running too hot for hours, and at a temperature just slightly above what you would call a warm afternoon, that ordinary metal component began doing something that solid metal is never supposed to do. It began to dissolve into the air. Not melt, not corrode, dissolve. It pulled the carbon monoxide molecules into itself and released a compound so stable in open air and so catastrophically unstable inside a human body that toxicologists have a nickname for it that they use only among themselves. They do not use it in official reports because it sounds too dramatic, but it is accurate. Voss pressed his pen against the paper and wrote 3 words at the top of his notes. Then he underlined them. The case that had looked like a mechanical accident, maybe a gas leak, maybe a ventilation failure, had just become something else entirely. Something that pointed not just to a faulty machine in one workshop in one city, but to a material that billions of people touch every single day without knowing what it is capable of when the conditions quietly shift around it. He closed the file, stood up, walked to the window, and looked out at the street below. People moving between cars, hands in pockets, fingers brushing metal surfaces without a second thought. He thought about how trust works, how we extend it automatically to the things we see every day. How familiarity feels exactly like safety, even when it is not. The metal on that workbench had not malfunctioned. It had not been misused. It had simply done what its chemistry always does when the temperature rises a little and the right gas is present. It had followed its own rules perfectly. The problem was that nobody in that workshop had known what those rules were. Voss had known. And now he had to explain it in a report that would be read by people who were going to find the explanation very uncomfortable. He sat back down and started writing from the beginning. Friends, if this story already has you thinking differently about the metal objects around you, hit subscribe and leave a like. It genuinely helps this channel keep going, and we are only just getting started. Voss began the reconstruction the way he always began reconstructions. Not with the moment of death, but with the moment everything looked completely normal. Because that is always where the real story starts. The workshop opened at its usual time that morning. 3 workers arrived, signed in, made coffee, put on their standard protective gear. Nothing about the shift felt unusual. The exhaust filtration components they were working with that day had been handled hundreds of times before by the same team. The metal parts were cool to the touch, heavy, smooth, with that particular dull shine that industrial alloys have under fluorescent light. Nothing about them suggested any reason for concern. The heating press nearby had been running slightly hot for about 3 days. Not dramatically hot, not hot enough to trigger a shutdown, just a few degrees above its calibrated range, the kind of drift that accumulates slowly in equipment that gets used hard and serviced infrequently. The workshop had logged a maintenance note about it. The note had not yet been acted on. The carbon monoxide was already present in the room before the shift began. The leak was in a poorly sealed exhaust fitting near the rear wall. The concentration was low, below the threshold of the fixed detector mounted near the ceiling, below the level where any human sensory system would register a warning. It was simply there, distributed evenly through the air, invisible and odorless, sharing the space with 3 men who had no idea it was present. What happened next was not dramatic. That is the part that Voss kept returning to in his notes. There was no sudden event, no visible reaction, no noise. The metal surface of the component sitting near the press began interacting with the carbon monoxide in the air at the elevated temperature, and it began producing a compound that the air in the room now carried alongside the oxygen, and the nitrogen and the coffee smell, and the faint mechanical oil that always hangs in workshop air. Nickel tetracarbonyl, colorless, odorless at low concentration, heavier than air, so it settled and spread slowly outward from the workbench. The 3 men breathed it in without any sensation of doing so. No burning, no taste, no reflex to hold their breath or move away. Their bodies received no signal that anything had changed. But inside, the compound was already moving through tissue, the way something designed specifically for infiltration would move. It was lipophilic, meaning it had a chemical affinity for fats, and cell membranes are built from fats, so it passed through them without resistance. It entered the bloodstream, and once it was inside, the heat of a living body, it broke apart. The bond between the metal and the gas destabilized. What had been a stable molecule in the open air became something else entirely inside living tissue. It released carbon monoxide directly into cells, and it deposited raw metal atoms, microscopic fragments of the element itself, into the most delicate biological environments in the human body. The lungs, the liver, the brain. The immune system, designed to identify and destroy foreign material, found metal particles embedded in soft tissue and did the only thing it knows how to do. It attacked. Not the metal specifically, because the metal was already dispersed too widely to target cleanly. It attacked the surrounding tissue. The inflammation that followed was not a slow process. It was catastrophic and accelerating. The alveoli began to fill. Blood vessels under chemical assault started to fail. Fluid built up where air was supposed to move freely. The first worker to show symptoms sat down and said he had a headache. He thought it was the start of a migraine. The second felt a heaviness in his legs that he described, in the brief time he had to describe it, as feeling like he had not slept in 2 days. The third said nothing and kept working. All 3 were already past the point where any intervention available in that room could have reversed what was happening inside them. Voss read the coroner's timeline 3 times. From first exposure to the point of no return was estimated at under 90 minutes. The compound had done its work so quietly, so completely without announcement, that the workshop safety logs showed no alerts, no emergency call, no indication that anything had gone wrong, until a delivery driver arrived and found the door unlocked and the lights still on. He set the report down and thought about the metal parts still sitting in the evidence locker. Cool, heavy, polished. Surrounded now by sealed plastic and warning labels. It looked exactly the same as it had on that workbench. It had not changed at all. It never needed to. This metal had been killing people for centuries before anyone understood what it was. And the truly disturbing part is that the people it killed first thought they had found treasure. Voss had a habit, when working a case that did not fit a clean explanation, of going backward, as far as the trail allowed, not just through industrial records and safety logs, but through the actual history of a substance. He believed that materials carry their behavior with them across time, that the way something acts today is not random. It is consistent. It is who that material has always been. So when the toxicology results pointed unmistakably to the metal in that evidence locker, Voss went looking for the earliest documented encounters between this element and the people who first pulled it out of the ground. What he found in those old records stopped him completely. Centuries ago, in the mountain regions of Central Europe, there were communities built entirely around ore extraction. Entire families, entire villages organized their lives around going underground and bringing up metal. The work was brutal, and the conditions were genuinely awful. Cold tunnels barely wide enough to turn around in. Oil lamps that gave more shadow than light. Air so thick with rock dust that men who worked those tunnels for years developed a chronic cough that never fully went away. But they did it because metal meant survival. Copper specifically. Copper was currency. Copper was construction. Copper was the material that built cathedrals and cast bells and made cannons that won wars. So when a team of miners in one of those mountain communities broke through into a new vein and found a rock with a deep reddish-brown color, heavy and dense and rich-looking, the reaction was immediate. These men knew copper ore on sight. They had spent their lives learning to read stone the way a reader reads a page. And this looked like the highest-grade material any of them had ever laid eyes on. They filled their baskets and hauled it up to the surface with the kind of energy that only genuine excitement produces. Then they put it in the furnace. What came out of that furnace was not copper. What came out was a thick white vapor that poured low along the ground because it was heavier than air, and it smelled like something between burnt metal and rotting plants. And within minutes, the men standing near the furnace were on their knees, their skin blistered on contact, their throats seized. The ones who had breathed the most of it did not recover. They died in the kind of distress that leaves witnesses permanently changed. And when the furnace cooled and the survivors went back to look for the metal they had worked so hard to extract, there was nothing there. Just a crumbling gray slag at the bottom that could not be forged into anything. Not a single gram of copper. Not a single gram of anything useful. They tried again with the next batch. Same result. And the next. Same result every time. For people living in that era, with no chemistry, no understanding of elements or compounds, no framework for thinking about why a rock might release invisible lethal vapor when heated, the conclusion that formed in their minds was not scientific. It was the only kind of conclusion available to them. The ore was not a geological formation. It was a trap. Something had deliberately disguised worthless and dangerous stone to look like the most valuable material they knew, specifically to lure them in, waste their labor, and destroy them when they got too close. In the folklore of those mountain communities, there was already a figure for this kind of malice. A spirit. Something between a trickster and a predator that lived in the deep rock and resented human intrusion. It was called by a name that translated roughly as the Old Underground One, a figure associated with deception and with the particular cruelty of giving someone exactly what they think they want before taking everything away. They named the ore after this spirit. They called it devil copper. And they began avoiding any vein that showed its characteristic color the way you avoid a road that has swallowed 3 travelers in a row. What Voss found remarkable, reading through these accounts in his office late at night with the case file open beside him, was the precision of the original intuition. Those miners had no chemistry, they had no instruments, but they had correctly identified something that took science several more centuries to confirm in formal terms. This material was not what it appeared to be. It obeyed different rules than the metals around it, and it would hurt you in ways you could not see coming. The name they gave it survived everything. It survived the age of superstition, survived the scientific revolution, survived the complete dismantling of every mythological framework those miners had used to explain the world. Today it sits in the periodic table between cobalt and copper, assigned its atomic number by the most rigorous, systematic process human knowledge has ever produced. And it still carries the demon's name. Not as a warning that anyone takes seriously anymore, just as a label. Just as a word that has lost its original weight through sheer familiarity. Voss underlined a sentence in his notes. Familiarity is not the same as understanding. He had written it as a reminder to himself, but reading it back in the context of those old mining records, it felt like something the mountain communities had already known and then collectively forgotten over the following centuries, right up until 3 men walked into a workshop on a Tuesday morning. The story of how this metal finally got its formal scientific identity is one that Voss had not expected to find relevant to a toxicology investigation. But the more he read, the more he understood that the identity of this element had never really been settled cleanly. It had been forced into the record by one person against serious resistance, and the circumstances of that forcing said something important about how we decide what we know and what we choose to ignore. In the mid-18th century, a Swedish researcher named Erik Sandal, working without institutional backing and without the kind of connections that opened doors in the academic world of that era, obtained a sample of the same ore that had been terrifying and killing miners for generations. Everyone with credentials and status had already looked at this material and declared it a known mixture of already cataloged elements. Copper contaminated with arsenic and iron and cobalt. Nothing new, nothing worth further investigation. The question had been officially closed by people who had the authority to close questions. Sandal did not accept the closed question. He was 28 years old. He had a small rented laboratory space, a set of basic tools, and a stubbornness that his contemporaries described in their letters to each other as somewhere between admirable and exhausting. He spent months on that ore. He removed the arsenic systematically, working through toxic fumes with primitive ventilation, risking exactly the kind of slow exposure that Voss had just spent 2 weeks documenting in a modern industrial context. He removed the sulfur compounds. He worked through every known impurity and stripped them out one by one until what remained at the bottom of his crucible was something that did not match anything in the existing catalog. It was white and hard and had a particular cool weight to it. It was strongly magnetic in a way that iron is magnetic, but copper is not. When dissolved in acid, it produced a green solution, not blue like copper, not the colors associated with any of the elements it had supposedly been composed of. Its melting point was wrong for every known candidate. Its density was wrong. Its behavior under heat was wrong. Everything about it said that it was not a mixture of known things. It was a single unknown thing that had been sitting inside that cursed ore the entire time, hiding behind the arsenic and the mythology, waiting for someone stubborn enough to find it. Sandal sent his findings to the major scientific institutions of the day. The responses he received ranged from dismissive to openly contemptuous. One prominent academy published a formal statement suggesting that his results indicated poor laboratory technique rather than a genuine discovery. The implication was clear. A provincial researcher without the right affiliations had made a measurement error and was now embarrassing himself by insisting otherwise. The correct thing to do would be to accept the correction and move on. Sandal did not move on. Instead, he did something that Voss found genuinely striking when he read about it. Rather than rename his element something neutral and academically respectable, something that would signal his desire to be taken seriously by the institutions that had rejected him, he reached back into that old mining folklore and pulled out the demon. He stripped the word for copper away from the original name and kept only the spirit. Not devil copper, just the devil. the name of the underground trickster officially registered in scientific literature as the identity of element 28. It was not a joke. It was not an accident. It was a very deliberate choice by a man who had spent months being told he was wrong by people who had not done the work he had done. And his choice said something that Voss kept thinking about as he sat in his office with the evidence locker key on the desk in front of him. Sometimes the people with the least authority are the only ones willing to look directly at what everyone else has decided is not worth looking at. And sometimes the thing they find has been right there the entire time, hiding in plain sight, wearing a familiar face, waiting for someone to finally call it by its actual name. Everything your physics teacher told you about how stars die was incomplete, and the part they left out changes the entire picture in a way that nobody in mainstream education seems particularly eager to discuss. Voss had not expected his investigation into 3 industrial deaths to take him into astrophysics. But that is the thing about this element. Every time you think you have found its boundary, the place where its story ends and something unrelated begins, you find that the boundary does not exist. The story keeps expanding outward. So when a colleague of his, a materials scientist named Dr. Petra Lang, who had been consulting on the case, sent him a research paper with a single sentence underlined in red ink, Voss read it 3 times and then called her immediately. The sentence said that iron was not the most stable atomic nucleus in the universe. The most stable atomic nucleus in the universe was a specific isotope of element 28. Voss had sat through the same physics classes as everyone else. He knew the standard explanation. Stars burn hydrogen into helium, helium into carbon, carbon into heavier and heavier elements through a chain of fusion reactions. And that chain terminates at iron, because iron is where the energy math stops working in the star's favor. Fusing lighter elements releases energy. Fusing iron consumes it. So the star runs out of fuel, the core collapses, the outer layers explode outward in a supernova. And iron is the final product of all that stellar cooking. It was presented as a clean endpoint, the crown of nuclear evolution, the most perfect thing matter could build. That story is missing a chapter. Petra explained it to him over the phone, with the kind of controlled excitement that scientists use when they are talking about something that genuinely thrills them, but that they have learned not to oversell in professional settings. She said to think about atomic nuclei the way you think about physical structures. A wall built from bricks and mortar. The bricks are the particles inside the nucleus, and the mortar is the energy that holds them together. The stronger the mortar relative to the number of bricks, the harder the structure is to break apart. You measure this as binding energy per particle. And it tells you how much force you would need to apply to tear that nucleus into pieces. Iron 56 scores very well on this measure. It is genuinely impressive. But nickel 62 scores higher. Not dramatically higher. The difference is small enough that it was overlooked for a long time and is still routinely omitted from textbook summaries because it complicates the clean narrative about iron being the end point. But on the scale of nuclear physics, small differences are everything. The universe does not round numbers. It operates on exact values. And the exact value that represents the tightest, most efficiently packed, most structurally perfect atomic nucleus that physics allows belongs to a specific form of the element that killed 3 men in a sealed workshop and scared generations of miners into abandoning entire veins of ore. The dying star, in its final moments, does not stop at iron. It keeps pushing. It squeezes out a last desperate round of fusion in conditions of temperature and pressure so extreme that the terms we use for them in everyday life stop meaning anything. And in that final burst, it produces nickel 62, the most complete thing matter knows how to be. After that, there is genuinely nowhere left to go. The process does not stall at iron the way a car runs out of fuel on a flat road. It reaches nickel 62 the way a river reaches the ocean. It arrives at the only place it was ever going to end up, and it stops because there is nothing beyond that point. Voss wrote this down slowly and looked at what he had written. The element that miners had called a demon and thrown into waste heaps for generations. The element sitting in an evidence locker 3 floors below him. The most stable structure the universe is capable of producing. He thought about Sandal, the stubborn Swedish researcher who had spent months being laughed at by established institutions before forcing his discovery into the record. Sandal had named it after an underground trickster because the institutions that should have found it had missed it entirely. Voss thought there was a certain additional irony in the fact that the universe's most perfect atomic construction had been hiding inside the most dismissed, most feared, most misunderstood material in the history of European mining. The question that followed immediately was the one Petra had anticipated before he could ask it. If this element is the true endpoint of stellar evolution, if it is being produced in the cores of dying stars across the universe, then why is it relatively scarce on the surface of this planet? Why are we not swimming in the most cosmically abundant form of stable matter? The answer to that, Petra told him, required going back to the very beginning of the Earth itself. Voss had been sitting at his desk when that conversation happened. Reading what came next made him stand up and walk to the window again. He had the same feeling he had experienced when he first read the toxicology results on the workshop case. The feeling of something much larger than he had anticipated coming into focus behind what had initially looked like a contained, manageable situation. The reason this element is so hard to find near the surface of the Earth is simple and brutal. When the planet was young, it was entirely liquid. A spinning ball of molten rock and metal with no solid crust at all, just an ocean of superheated material slowly separating itself out according to the rules of density and gravity. Light material floated, heavy material sank, and it sank all the way down through thousands of kilometers of increasingly hot and pressurized rock until it reached the center and stayed there. The thin rocky shell we live on, everything from the deepest mineshaft humans have ever dug to the soil in your garden, is essentially the light fraction, the overflow, the geological foam that was not heavy enough to follow everything else down toward the core. All the heavy metals, the gold and platinum and iron and nickel, were supposed to be unreachable, locked away at a depth where no drill has ever gone and no drill ever will. The surface should have been almost entirely stripped of them, and it largely was, except in specific places where something went catastrophically wrong. Voss pulled up a satellite image on his screen, a vast oval depression in the Canadian landscape, so large that from ground level you would never know you were inside it. Over 100 kilometers across, the shape of something that hit hard and hit once and left a mark that the planet has not finished processing even after nearly 2 billion years. An asteroid, not a small one. The kind of object whose impact released energy that circled the planet in the shockwave, that turned solid rock into vapor in the first fractions of a second, that excavated a hole in the crust deep enough to reach material that had no business being anywhere near the surface. The asteroid itself was loaded with heavy metals. It had formed in the same stellar environment that produces nickel-62. It had been carrying that cargo through the solar system for billions of years before it intersected with the early Earth, at a speed that made the collision less like an impact and more like a detonation. When the resulting melt lake cooled over millions of years, it left behind ore concentrations so rich that they are still being extracted today at an industrial scale. Enormous machines the size of buildings crawling through a crater left by an event that would have been unsurvivable for anything alive at the time. The deposit exists because something from space hit this planet hard enough to partially undo the separation process that was supposed to keep this metal locked away forever. Voss looked at the image for a long time. Then he typed a note into his case file. He wrote that the workshop in which 3 men had died contained material that had originally arrived on this planet as part of a cosmic collision. That the same element which the most rigorous nuclear physics in the world identifies as the universe's most perfectly constructed atomic structure had reached the surface of the Earth only because of a catastrophe so large it reshaped the continent around the impact site. There was a second major source, not from space this time, but from directly below. And what had happened there made the asteroid look, in some respects, like the less destructive of the two events. The only reason you are alive right now, the only reason there is breathable air on this planet at all, is because of a boiling ocean of liquid metal 6,000 kilometers below your feet. And nickel is the thing keeping that ocean from freezing solid. Voss had spent the previous evening going through Petra's notes on the second major surface deposit. The one that had nothing to do with asteroids and everything to do with what happens when the planet's interior decides to tear itself open from below. That deposit existed because of a mantle event so violent that it had poisoned the atmosphere and erased the majority of species alive at the time. The ore was there because the Earth had, in geological terms, briefly turned itself inside out. And the nickel that came up with all that magma had been sitting near the core, exactly where heavy metals go when a planet forms and separates itself by density over millions of years. Which meant that every surface deposit of this element, whether delivered by an object from space or vented up through a mantle rupture, had one thing in common. It had escaped from a place where, by all the normal rules of planetary formation, it was supposed to remain permanently. The core. The deep interior. The place that geophysicists describe in terms that make it sound like another world entirely. Because in almost every meaningful sense it is. Petra had sent him a second paper, this one from a geophysics journal, and Voss had read it slowly, because it required the kind of sustained attention that you give to something when you sense that it is going to change how you think about a larger question. The paper was about the Earth's core and about what it actually does, not in the sense of what it is made of, but in the sense of what its continuous behavior produces for everything living on the surface above it. The core is not inert. It is not just a dense ball of compressed metal sitting quietly at the center of the planet. The outer layer of it is liquid, an ocean of metal alloy under pressure that human engineering cannot come close to replicating. At temperatures comparable to the surface of the sun, churning constantly because of the temperature difference between its own internal heat and the relatively cooler mantle surrounding it. Hot material rises, cools slightly, sinks again. The whole system rotates, and because the planet is spinning, that rotation gets twisted into enormous spiral currents that move through the liquid metal in patterns that take thousands of years to complete a single cycle. And because that liquid metal is an exceptional conductor of electricity, all that movement generates current, and current generates a magnetic field. The field extends outward from the core, passes through the mantle and the crust, breaks through the surface, and reaches far into space in a shape that wraps around the entire planet like an invisible shell. You cannot see it, or touch it, or smell it, but without it, this conversation would not be happening, because nothing that produces conversations would exist here. The sun is not the gentle, warm light that it appears to be from the surface of a planet with a functioning magnetic field. It is a continuous source of charged particle radiation, moving outward in all directions at enormous speed. Without a magnetic field to deflect that radiation, the upper atmosphere begins to erode, slowly at first, then faster. The lighter gases escape into space. The heavier ones follow over geological time. The oceans evaporate into a thinning atmosphere. The surface temperature becomes unlivable. Everything that depends on liquid water and breathable air disappears, and what is left is rock and dust and silence. Voss had seen images of Mars in the paper. Petra had included them deliberately. Mars has a core that cooled and solidified too early in the planet's history. Its magnetic field collapsed. The process that followed took millions of years, but was, in terms of outcome, total. The planet that may once have had liquid water on its surface is now a frozen desert where the atmospheric pressure is less than 1% of what you are breathing right now. The Sun did that. Not through any dramatic event, but through the patient, continuous pressure of radiation against a planet that had lost the thing keeping it safe. Earth has not lost that thing. Not yet. And the reason it has not is partly because of the composition of the core itself. Iron alone, under the pressures present at the Earth's interior, would tend to crystallize into a solid structure much more readily than the alloy that actually exists there. The addition of nickel changes the physical behavior of the mixture in a way that keeps the outer core liquid at conditions where pure iron would begin to lock up. It acts as a kind of thermal and structural buffer, lowering the threshold at which the metal solidifies, allowing the churning and the currents and the field generation to continue across timescales that dwarf anything in human history. The demon from the mining folklore, the trickster that poisoned workers and refused to yield useful metal, the element that killed 3 men in a sealed workshop and sat in an evidence locker 3 floors below Voss's office, was also the reason the planet retained its atmosphere. It was the antifreeze in the engine that kept the magnetic shield running. The miners who cursed it and threw it into waste heaps had been, without knowing it, standing on the surface of a planet whose habitability depended on an enormous quantity of the same material buried at the center. Voss sat with that for a while. Then he moved to the next section of his notes, because the story was about to take a turn that he found significantly less comfortable than the physics. Nobody likes being told that something sold to them as clean and responsible is built on a foundation that is neither of those things. And the document that Petra had forwarded to Voss from an environmental consultancy source was exactly that kind of information. It was an internal supply chain audit for the battery manufacturing sector, covering the extraction and processing of cathode materials for high-capacity cells, the kind of batteries that go into the electric vehicles being marketed globally as the solution to the environmental costs of fossil fuel dependence. The audit had not been published. The covering note from Petra's source was brief. It said that the figures in the document were accurate, and that the decision not to publish had been made at the legal department level. Voss printed it and read it front to back without stopping. The core of the problem was straightforward. The cathode in a modern high-performance battery, the component that actually stores and releases the energy that moves the vehicle, is built primarily from a processed form of element 28. Not lithium, which gets almost all of the public attention and carries almost all of the marketing weight. The lithium moves the charge around. The nickel holds it. A single vehicle of the type being sold as an environmental statement contains between 40 and 60 kilograms of refined nickel sulfate, and producing that material at the scale now being demanded by the global transition away from combustion engines requires a supply chain that the audit described in terms that were very difficult to read without feeling a specific kind of anger. The ore being processed for this purpose in the main production regions is low-grade. It is embedded in tropical laterite clay, a reddish surface deposit that is abundant but contains the target metal in concentrations too low to extract through conventional smelting. The process developed to handle it involves loading millions of tons of excavated material into pressurized vessels and flooding them with concentrated sulfuric acid at temperatures and pressures far above anything that occurs naturally on the surface. The acid dissolves the metal out of the clay. What remains is an enormous volume of liquid waste that is hot, highly acidic, and loaded with dissolved heavy metals and other compounds that do not belong in any natural water system. The audit documented where that waste was going. Some of it was stored in containment ponds behind earthen dams that had a documented history of structural failures during heavy rainfall events. Some of it was being discharged through permitted and unpermitted channels into coastal marine environments. The satellite images included in the audit showed the watercolor around the discharge zones in a way that required no technical expertise to interpret. It was the color of something dying. Coral structures that had taken centuries to develop were documented as being smothered under layers of fine acidic sediment. Fish populations in the affected zones had declined to the point where the communities that had depended on them for generations were reporting near-total collapse of their traditional food source. And the energy powering all of this, the electricity running the acid pressurization systems and the pumps and the processing facilities and the transport infrastructure, was coming from coal. Not from the renewable sources that the end product was supposed to help replace. From coal, burned in large quantities, producing the same category of emissions that the finished battery was being sold as an alternative to. The audit included a calculation. It compared the carbon output of producing one battery pack through the current supply chain against the carbon savings generated by replacing a combustion vehicle with an electric one over a standard operating period. The calculation included a regional factor for where the vehicle would actually be charged. In regions where the electricity grid still relied heavily on fossil fuels, the crossover point, the moment at which the electric vehicle had offset the environmental cost of its own production, was measured not in months, but in years. In some scenarios, the crossover point exceeded the expected operational lifespan of the battery. Voss read that paragraph twice. Then he looked at the covering note again. Legal department. He understood why it had not been published. He also understood something else, something that connected back to everything he had been reading about this element across the previous week. The story of nickel had always been the same story underneath. The story of something that looked different from what it actually was. The miners had found what looked like copper and got something lethal. The scientific establishment had found what looked like a known mixture and missed an entirely new element. The consumers buying vehicles with green license plates were buying what looked like an environmental solution and getting a supply chain that had simply moved the damage somewhere less visible. The exhaust pipe had not been removed. It had been relocated to a coastline on the other side of the world, where the people living next to it did not have the same platform to talk about what was happening to their water. If you tried to remove every trace of nickel from your body, you would not become healthier. You would be dead within weeks, and the thing that killed you would be your own digestive system turning against itself. Voss had not expected the biological section of Petra's research package to hit him the way it did. He had spent the previous days moving through geological timescales and planetary physics and supply chain documents, and somewhere in all of that, the human body had started to feel like a small and almost incidental thing. Then he read the biology notes, and the scale collapsed back down to something uncomfortably personal. The connection point was an experiment that researchers had conducted several decades earlier. The goal was simple in concept. They wanted to know what happened to living organisms when this element was completely eliminated from their environment. Not reduced, eliminated. They built housing units from materials that contained no trace of the metal. They filtered the air, purified the water, and formulated synthetic feed from which every detectable quantity of the element had been chemically removed. Then they introduced test animals and monitored them carefully. The animals did not thrive. Within a relatively short period, they began showing signs that looked nothing like the toxic exposure symptoms Voss had been documenting in the workshop case. No inflammation, no immune overreaction. Instead, a quiet systemic failure. Their blood cell counts dropped. Their ability to process iron from food collapsed, even when iron was provided in adequate quantities. Their livers changed color and began to fail. Their bone development slowed, and their joints showed structural abnormalities. The end, when it came, was not dramatic. It was the kind of deterioration that happens when something fundamental to the maintenance of life has been quietly removed and the system runs down like a clock that has not been wound. The reason came down to a single enzyme. an enzyme that lives in the gut and whose specific job is to break down urea, a toxic byproduct that the body produces continuously as it processes protein. If urea is not broken down efficiently, it accumulates. The blood chemistry shifts. The liver works harder to compensate and eventually cannot keep up. The body begins, in effect, to marinate in its own metabolic waste. The enzyme that prevents this has a very specific structural requirement at its active center. The part of the molecule that actually does the cutting, that grabs the urea and dismantles it, is built around two ions of element 28. Not iron, not copper, not zinc. This particular metal, in this particular configuration, and nothing else will substitute for it. Voss wrote in his notes that this was the most precise biological trap he had ever encountered in 20 years of working with toxic substances. The same element that had killed 3 men in a sealed workshop by generating invisible compounds that dissolved through cell membranes and deposited raw metal inside living tissue was also running a non-negotiable maintenance function inside the gut of every living person on the planet. Too much of it reaching the wrong place, and the immune system tears the surrounding tissue apart, trying to destroy the contamination. Too little of it present in the diet, and the digestive system begins poisoning the body from the inside with its own waste products. The safe corridor between those two outcomes is narrow, and we navigate it every day without thinking about it, because the system has been calibrated by biology over an enormous span of time. He thought about the miners again, the ones who had refused to touch the ore, who had spat on the ground and walked in the other direction when they found the characteristic reddish veins in the rock. They had been trying to create distance between themselves and something they understood, correctly, to be dangerous. What they could not have known was that the same material they were avoiding was already inside them, embedded in the chemistry of their own bodies, doing quiet, essential work that kept them functional. You cannot create distance from something that is already part of your architecture. The workshop victims had inhaled a lethal concentration of a compound that this element produces under specific conditions. They had died because of its chemistry. But the enzyme in their guts had been running on its ions that same morning, breaking down metabolic waste, keeping their blood clean, doing the work it had always done. The element had been killing them and maintaining them simultaneously. And the difference between those two outcomes had been nothing more than concentration, location, and the specific chemical form in which the metal was present in their bodies. Voss closed Petra's biology notes and sat quietly for a moment. Then he picked up the phone. The last piece of the case was the one that Voss had been putting off, not because he did not understand it, but because it required him to hold two completely contradictory things in his mind at the same time, and the discomfort of doing that was harder to resolve than any of the chemistry or geology had been. The medical application existed because engineers had discovered that a specific alloy combining this element with titanium behaved in a way that no other material matched for a particular surgical purpose. The alloy had a property called shape memory. You could cool it down, deform it into a different shape, and it would hold that new shape until it was warmed back up to body temperature. At that point, it would return, with significant force, to its original programmed configuration, precisely and repeatably every time. The application that had been developed from this property was a small mesh tube used in cardiac surgery. A surgeon could compress the device into a thin profile, thread it through a blood vessel on a catheter, navigate it to a point of dangerous narrowing near the heart, and release it. Warmed by blood at normal body temperature, the device would expand into its original shape, pushing against the vessel walls, holding the passage open, restoring blood flow. The procedure was now performed hundreds of thousands of times every year globally. People who would otherwise have experienced fatal cardiac events walked out of hospitals and went home to their families because of a device that was more than half composed by weight of the same element sitting in Voss's evidence locker. The reason the device worked inside a living body without triggering the kind of catastrophic immune response that the biology notes described in such detail was a coating. A layer of titanium oxide only a few atoms thick applied to the outer surface during manufacturing. That coating was chemically inert. It sat between the living tissue and the metal core and prevented the ions from being released into the bloodstream. The immune system saw the coating and found nothing to react to. The device was accepted. It bent and flexed with the movement of the vessel, tens of millions of times over its operational life, without breaking, without corroding, without changing in any way that the body could detect. As long as the coating remained intact, Voss had requested the manufacturing quality data for the device as part of his broader investigation into industrial applications of the element. What he found in those documents was not alarming in any dramatic sense. The defect rates were low by any standard comparison to other medical devices. The coating process was well controlled. The incidence of adverse events attributable to coating failure was rare. But rare, in a procedure performed hundreds of thousands of times annually, still produced a number. And that number represented people in whose arteries the coating had, at some point after implantation, developed a microscopic compromise, a scratch during insertion, a manufacturing variation too small to detect visually, a fatigue crack in a vessel that moved differently than the modeling had predicted. Whatever the mechanism, the result was the same. The barrier failed. The metal below was exposed to blood. The ions that followed were the same ions Voss had been documenting all week. The same chemistry, the same behavior inside living tissue. The difference was that this time they were not arriving through inhaled vapor in a sealed workshop. They were being released slowly and continuously from a device implanted directly into the wall of a major artery, carried by blood flow to every organ in the body, accumulating over months or years before symptoms developed to a level that connected back to the implant. Voss finished writing his report on a Thursday afternoon. He filed it without editing the conclusion, which his supervisor would find uncomfortable, and which accurately described the situation he had documented. The element was present in every layer of the world he had investigated. It was in the industrial workshop that had killed 3 people. It was in the asteroid crater, providing raw material for global manufacturing. It was in the battery supply chain, destroying marine ecosystems on the other side of the planet. It was in the gut enzyme, keeping people alive. It was in the cardiac device sitting in arteries right now, in people who were at that moment doing ordinary things. Cooking dinner, walking a dog, watching something on a phone whose battery cathode was built from the same material. He had started the investigation looking for the cause of 3 deaths in a sealed room. What he had found instead was a single element threaded through every scale of existence he had examined, from the atomic nucleus outward to the planetary core, from the chemistry of digestion to the structure of the magnetic field keeping the atmosphere in place. It had not been introduced into any of these systems by human decision. It had been there before the decision-makers existed. It would be there after the last one was gone. The report's final line read as follows: "We did not integrate this element into our civilization. We built our civilization inside the space it left available to us. And we have been calling that arrangement mastery ever since." Here is the thought that stayed with Voss long after he filed that report. And it is the thought that stays with me now, having traced this element from a medieval mining curse all the way to a cardiac surgery suite. We live in an age that is extraordinarily good at presenting solutions that look clean from the angle we are shown, and catastrophic from the angle we are not. The green vehicle and the poisoned coastline. The life-saving implant and the invisible coating failure. The familiar metal in the pocket and the compound it becomes when the conditions quietly shift. The pattern is not accidental. It is what happens when we optimize for the appearance of control rather than the reality of understanding. So here is the question I want you to sit with, and I genuinely want to know what you think. If the most stable structure in the universe is named after a demon, and we have built our medicine, our technology, our planetary survival, and our own biology around it, without ever fully understanding it, what else are we living inside right now that we have simply decided to call safe because looking more closely feels inconvenient? Write your answer in the comments. I read every one of them. If this story made you think differently about something you thought you already understood, leave a like and subscribe. It is the most direct way to tell me that this kind of work is worth continuing, and there is a great deal more of it to come.